Now what you should be focused on is on chapter 7 and chapter 8, which will be graded in exam number 3, and then we'll have the final exam on the mid of December. So hopefully today after during the class, I'm gonna go and try to see when the final exam, we have already the calendar for it. From what I saw, you're gonna have good amount of time to complete it because it's the whole course. All right. But I will make it, and I will do a review session before that. Okay. I'm guessing mostly the applications, the problems. With this topic, chapter 7 is mostly a theoretical or conceptual sort of a chapter, because there are many equations, there are many ways to quantify it, but they go beyond the scope of the course, which is mostly to explain you about the electric charge, current, applications of current in circuits, then go into capacitors, more complex circuits, again, maybe just Ohm's law and power radiated by resistors, and then go into electromagnetism and waves. So 2 chapters where we're going to be discussing topics that are normally discussed and introduced in physics 2, in advanced physics, right? And it takes a whole semester because there are a series of calculations with vectors, in circuits, with Kirchhoff laws and all. But right now, the objective is to understand the concept of charge. So, in the previous topics, we discussed units, mechanics, energy, forces, a little bit of vectors. We discussed matter, fluids, the states of matter, heat, temperature, and waves and oscillations. So that's all related with mechanics. Maybe when you talk about matter, fluids, and gases, it's more about the physics of matter, right? Now we're going to go into a more microscopic study of matter, which is the idea of charge, electrons, protons, neutrons, the atom, the nucleus of the atom, the structure, and why we have different substances with electrical charge, positive or negative. The best example is what you are seeing right now on the screen. When you have pieces of paper and then you wrap, it can be a rod of amber or plastic, right? I'm pretty sure you guys have done this in a school, in elementary or middle school, where you can see that you can attract. It's not a big stick, although that's the commonly idea, right? That they stick. The reason they get towards the bar that you see there is because of an electric charge, which is just a physical property of a substance, right? Due to the charge of subatomic particles, the excess of amount of some subatomic particles, in this case electrons, right? You can have an excess of electrons, and then the body, the bar, the whatever, will have an excess of negative charge. So the overall charge of the material will be negative. You can have excess of positive charge of protons, then the overall charge will be positive. The label for charge is Q, and the SI unit for it is coulombs. Although we normally use prefixes like nano, pico, micro, or sometimes millicoulombs. Why is that? Because the charge per se of any material, since we are discussing about the excess of either protons or electrons, and because we know that the charge of the electron is the same as the charge of the proton, then we can say that the overall charge of a body is is the multiple, it's an integer multiple of the charge of the electrons array. So you can have an excess of 2 electrons, 3 electrons, never a half or a quarter. It's always an integer, a whole number. The same with the protons. Now, what you're seeing right now is the, I want to say, the old model of the atom. You probably have seen also that in a chemistry book in high school or middle school, when you discuss the nucleus of the atom as the part that is the most dense part of the atom, where you have the protons and the neutrons, and then you have the electrons orbiting. That's the concept of orbitals in chemistry, right? When you have the orbitals and then you have the electronic configuration SPDF. So every electron has a different atomic number. That's how we arrange elements in the periodic table, by increasing atomic number. And then you have the different periods and groups, right? But this model is actually not correct. It's an old model based on the idea of the Bohr model. The Bohr model was the first one that sort of predicted what we were observing. What we were like, it predicted. It was a very elegant model for the electron going around the nucleus. But he said it was a circular orbital. Then it was corrected into elliptical orbits. And that's why they call them orbitals, not, for example, Bohr, he defined this Bohr radius for different positions of the electron, right? Because the electron can be ionized by giving it energy. So it can have electronic jumps, right? So that is studied in chemistry. That's all because of physics, by the way, right? By the energy absorbed by the electron, then the atom gets ionized and it can release energy or absorb it, and then there can be an electronic jump. But that was all good up until the moment where we were introduced to the Schrödinger equation, and then we know now that there is something called an electronic cloud, an electron cloud. And then due to the Heisenberg uncertainty principle, we know that we will never be accurate enough to predict the velocity and position of the electron with 100% accuracy. You can predict, you can have the probability of where the electron might show in a given orbit, let's keep calling that name, but you will never know the exact magnitude of the motion. All right? So that's that, okay? And the thing is that, you know, when we talk about oscillation, something that we didn't discuss is that every piece of matter has a wavelength associated, especially subatomic particles. It's been proven by the interference experiment, like the Young WSD experiment that I introduced you with light. We know that matter also has a wave behavior. And if you have matter going really fast, then you can have a wave sort of behavior there. Okay. And also depending on the mass, right? So the mass of an electron is very tiny, and then you can actually get the lower the mass, the way lower the mass, the easier it is for us to see or to predict or to observe the evidences of a wavelength, of a particle behaving as a wave. All right, that happens with electrons a lot. So, well, that was a brief introduction to a little bit of quantum atomic physics, and we need that to understand this. The fact that you can wrap a neutral bar, it can be a insulator, by the way, it can be made of plastic, and then you remove electrons. There is a transfer of electrons from the bar to the cloth, which can be made of wool, by the way. Depending on the material, you can also have a transfer of electrons from the wool to the bar. That normally happens with amber. If that's the case, then the amber bar will get a an excess of negative charges, right? If you wrap glass with silk, then the glass will acquire a net, so you will remove electrons from the glass, and they will go to the silk. So there is always an excess of electrons in one or another material, and there is always electrons being transferred from one material to another. When you lose electrons, your overall charge, your net charge is positive. So that's why you see the positive and the negative there. So that's a good exam question there, by the way, right? Or a quiz question, right? What happens when you wrap, what is being transferred? You are transferring electrons. So one of the materials gets positive, the other material gets negative charge. Okay? That's very important. That's something that you need to realize. You can also do that by combing your hair, right? When you comb your hair, you can charge the comb in the same way. Let's do this later. Okay, as I said, we can do a whole bunch of calculations, but for now, I want you just to understand the physical characteristics of the force between electric charges. And the best way is to show you this slide, where they give you the positive and negative, and two positive, and you can also have two negatives in there. If that's the case, then between the positive and the negative, you have a force of attraction. Opposite poles attract. That's where that phrase comes from. And that force was studied by Coulomb. That's why it's called a Coulomb's law. He realized that the force is proportional to the multiplication of charges and inverse proportional to the square of the distance. That will remember you to the gravitational force. When we did gravitation, Newton's law of gravity, we introduced the idea of gravitational field and gravitational force. The Coulomb force has a similar characteristic. Instead of mass, you have Q's, and now the distance is between the subatomic particles or the charges. When you have like charges, they repel. Positive and positive repel, negative and negative repel. Okay? Right now, everything we're talking about is about static charges. So we're not talking about electricity per se. So electricity, guys, happens when you have a flow of electric charge. Now, to be more precise, it's a flow of electrons. However, when electricity was studied, we're talking about 200, 300, 400 years ago, it was thought that the charges moving were actually positive charges. So that's when we're going to get into the idea of the direction of current, right? Now, I said that the electric force is proportional to the multiplication of charges and inverse proportional to the distance squared. That's what you have there. But what is the constant of proportion? It's there. 9 times 10 to the 9. Newtons per coulomb square, newtons meter square per coulomb square. So, can we do calculation? Yes, you can, but you have to remember that the force is vector. While the charges are on the same plane, it's easy. You can do that, right? But if you have charges on a different plane, then you start getting into a more complicated scenario. Alright? Let me show you a calculation right now, and then let's see what happens when you double, you triple a charge. But see how I'm talking about the electric force. I always like to bring gravitation into this because they are very equivalent. We have a gravitational force, a force due to gravity, and actually this allows students to understand the idea behind gravitational field. Because we can do experiments in the lab where we study something called an electric field. The best way to understand an electric field is by understanding gravity. Gravity is acting all around us due to the Earth. The Earth, because of its mass and radius, it exerts a gravitational pull towards all of us, which is why objects fall towards the ground. In electricity, there is something called an electric field, which exerts not a gravitational force, but an electric force, either attractive or repulsive. It depends on who is the source of the electric field, which is normally a positive charge. But you can also have a negative charge, though. So what happens there? So let me show you a calculation. Okay, you know what I saw the other day as well? I was taking a look at the recording, and I didn't like how in the recording it doesn't seem very clear. So today I'm going to check this recording, and if not, I'm going to have to see with the admin, because I see all you guys on the screen, and I see myself in a very small window. So I mean, you can still hear what I'm saying, but it's not very clear what is on the whiteboard. So I'm right now changing some of these settings. So if it doesn't work, I will take a look and see what's going on, because for the review, for exams and the final, you do need to see the whiteboard. The other solution will be if I go to the observatory, right? And do that class from there. Anyway, so let's just show you very quickly. We're not going to do crazy vectors in here, okay? We're just going to do a problem, not a problem, an exercise, where I give you a positive charge and a negative charge. This positive charge will have a charge Q of, and here we're going to practice some prefixes. Let's say 6 microcoulombs, and in here Q1, and here Q2, let's say is equal to negative 5 microcoulombs. Now I'm going to say that the distance between the charges let's say is we're talking about very small charges. They could be, you see what happens. So I really need to see what's going on with the, so I cannot be checking all that all the time anyway. So again, we're looking at distances that are very small, not like meters or kilometers. So I will just use here 0.02 meters. So 2 centimeters. The equation, the way you use it, is that the Coulomb force, or the force, the way you're going to do it is like this, guys, because you want the magnitude first. K, magnitude of Q1, magnitude of Q2, divided by the distance squared. And then I want you to draw. How does the force act on a positive charge there? And it will act like this. Right? So that force is like that. And for this guy is like that. So that's the force there. But that force is a vector. So for the positive charge, the force is a positive vector going to the east, to the positive x. For this vector, we'll have a negative direction. But here we care about the magnitude. So how do I get the magnitude? 9 times 10 to the 9 Q1, but I don't write 6. I write 6 times 10 to the negative 6 because of micro. 1 micro is 10 to the negative 6. Negative 5 micro, but I have the absolute value. So I just write 5 divided by the distance. Now, for that, my recommendation will be to write it in scientific notation. So this is 2 times 10 to the negative 2. So here I will have now 6 times 5, 30 times 9, 270. Now, 10 to the 9 times 10 to the negative 6 is 10 to the power of 3. Times 10 to the negative 6 is 10 to the negative 3. 2 squared, 4. 10 to the negative 2 squared, 270 divided by 4 is 67.5. 10 to the negative 3 divided by 10 to the negative 4. If you remember your rule of exponents, law of exponents, negative 3 minus minus 4, 1. So this is equal to times 10. So the answer will be 675 newtons. But that's the magnitude of the force. How do I get the direction? Here you will say 675 in the positive x direction. Here will be the same in the negative x direction. So that's simple. That's the only thing that you need to know from this. Then they ask you what happens if you double the charge. If you double, and this is 12, then the force, based on what we just did, gets doubled. So you have double that force. If you double the distance, be careful though. Look what happens if you double the distance. Because the Coulomb law is K Q1 Q2 over distance squared. If now you have twice the distance, you will have K Q1 Q2 over double the distance squared. 2 squared is 4. So you get the same force, but now divided by 4. So it gets reduced by a factor of 4. Okay? There you are. Okay. So that's with forces though. But to be honest, it's not very, it's important, but to study the properties of static electricity, because this is called actually static electricity, electrostatics. We need to understand the idea of an electric field. And the best way is if you understand the idea of gravity, because they both are fields. Gravity is the gravitational field. Electric field, or in electricity, we talk about the electric field. The electric field is a property of every charge. As long as there is charge, there is an electric field. The only difference is the direction. So again, we're going to talk about point charges for that. So for the electric field, right, you have a positive charge, which is emanating field. We call them field lines. The way you see them is like this. That's also in the slides, by the way. In every direction, they go away of the charge. The way we observe this in a lab is by drawing what we call equipotential lines, which in this case, because of symmetry, it will be like that. And then the electric field keeps going. But you know what? It gets weaker as the distance is farther and farther from the charge. So very close, very similar to the gravitational pull, right? As close as you are from the sun, you won't feel its attraction, or the earth, right? The closer we are towards the earth, the easier we're going to be captured by its gravitational pull. In the case of a charge, the farther you are, you won't really feel it, or another charge. Because how do we test the existence of an electric field? So this is the electric field, by the way. We test it by placing a test charge that is always positive, Q naught. That is a test charge. And what we observe that this charge will move away. It's positive, right? That's a positive. So it will move away in that direction, given a force, an electric force. So what is then the definition of an electric field? The electric field is equal to the electric force per unit charge. In this case, Q naught, which is in units of newtons per coulomb. Okay? That is what we can study in the lab. By understanding the idea of an electric charge and the electric field. Now, what about a negative? So here, I can draw also a negative charge. The negative charge will have an electric field like this, in an opposite direction to the positive charge. That's the electric field for the negative. And how do we study the interactions between negative and positive? There is something called electric field lines. So as this leaves the charge, it goes towards the negative. As this leaves the charge, it goes towards the negative. You can have another one leaving, entering, and then another one leaving, entering. And then you can have more leaving, more entering. Those are the equipotential lines between the positive and negative charge in there. All right. Okay, let me share with you guys what I'm talking right now about. So, the electric field is a vector. It has direction. And that's how we test Coulomb's law. That's how we test the existence of a charge, of a source charge. The electric field has to be due to a source, which in this case can be Q. The positive and negative that you see there right now are the test charges. You place them in a region with electric field and they will move away or towards. You know what? There are a few things that we can also talk about when we discuss about the electric field or charges. The best one will be the Van der Graaf generator. a Van de Graaff generator, which we have here, let me show you very quickly. Is this. So, Van de Graaff generator, all right, and let me just unshare this for a bit. It's a device that you probably saw in the school, right? So the nice thing about this guy is that, well, I'm not gonna plug it in because especially right now it's too close to myself and that's not, but you have a metallic hollow, but it has a empty, has a hole in there, and this metal conductor, and inside this steel there's a belt. When you plug it in, you will create motion, mechanical motion of the belt rubbing against here. You see that there? Oh, there. That process of rubbing, as you know already, will create static charges in here. What we know is that there will be sparks going around. And we can use another conductor to create sort of like a mini lighting, right? The idea with this device is to create static charges and high voltages. It's just to demonstrate how static charges are produced due to rubbing and how much charge you can create depending on the speed of it. Now, why do we have sparks in the first place? Because this is a conductor. So a very important difference between a conductor and an insulator is that in a conductor like this, when you have charge, it will be all distributed on the surface of it. If you have an insulator like this, for example, the charge will be distributed all around its volume. So for an insulator, inside insulator, here, there's no charge. So inside here, there is no field. To have a field, you need to have charge. So the field is solely due to the charge on the top of this conductor, which it can be strong, right? Now, you can place a charge and it will experience a force. It can be either positive and it will repel it, or you have a negative charge, it will go towards that, right? The best way to do the experiment with this is by placing yourself on a wooden table, which is an insulator, and place your hands here. Because that is an insulator, the charges will go to your body and they will go towards your hair and then they will go like that, right? You probably have seen that in a documentary, right? So that's a very interesting way to show you guys how, and that's probably, I believe that's the biggest, I don't know where it is in the museum here in the US, the biggest electric Van de Graaff generator, right? And you know what? That guy is protected. Even though there's a spark there, he's holding, I believe, a mini conductor there, and he's creating the spark. Now, how come he's protected? Because what he is using right now, he's in a Faraday cage. A Faraday cage is an electrical insulator. Not insulator, it's like an electrical shield. Alright? The best way to explain it is like this. Okay, you guys will like this example. Is the reason why Magneto uses a helmet to protect himself from Xavier. If he's using a helmet, there is no way brainwaves, right? Well, in the comics, right, can go within the helmet. In this case, the cage is something like a helmet, and then radiation cannot penetrate it. It's the same idea of when you go under a bridge. Well, nowadays probably with the quality of the signals that doesn't happen, but you probably experience that with your phone. For example, I'm right now in a lab with a lot of electrical equipment, and it's inside a building. So the signal of my phone is not as strong as it is outside. That's because the whole building can act like a sort of Faraday cage. All right? So that's another good example of electricity and electrostatics, right? Which is why people rely a lot in Wi-Fi. And the example above, under the bridge, is the idea of you losing radio signals, right? You're listening to the radio, and then when you are under a tunnel, and that probably happens, your GPS, your radio, for example, the Holland, right? The Holland Tunnel that connects New Jersey with New York, normally I don't get any signal there. That's because the tunnel is a Faraday cage. All right? It's always some sort of explanation. It's not magic. All right. So how do we use the electric field? Right? Because a lot of these concepts are sort of abstract. I mean, I can show you the Van der Graaf generator and that's okay, but you are used more with electrical devices, current, voltage, electricity. So that's when we have the idea of a capacitor. And that's what you have in front of you. All right? We can have capacitors that are able to store electric energy. All right? So the idea is to have parallel plates like they show you in there. And then you can have, well, in this case, they are showing you an application with a dielectric. But we're going to assume that between the plates, a positive and negative plate, there is no, there's nothing, there's just air. So there's an electric field flowing. Due to the electric field, right, you can have, let's see here. You can actually have batteries like they show you there. Okay? Let me actually show you the example of what I'm talking about. It looks like this actually. Okay? The only difference is that in a parallel plate capacitor, which actually they show you there on picture A, figure A, they show you a negative and a positive. The only way you're going to get a field is if you have a negative and a positive plate. So the electric field goes from positive to negative. Always. Alright? And you saw it on the whiteboard when I did that positive to negative charge. That's how the electric field works. But the other thing is that the electric field inside a parallel plate capacitor can be used to store electric energy. And that's where we get the idea of voltage. Alright? Let me just show you very quickly. Oh wait, I was not sharing here. I was actually trying to share this. There, that. Okay? So in figure A, that's what I'm talking about, parallel plates. I think before I was talking about, oh there. That's what I was trying to show you before, the Faraday cage. Alright? So that's the Faraday cage there, and there's a Van der Graaf generator there. Okay? So in the parallel plates, you can have an electric field stored. Okay? And that's the idea behind capacitor and capacitance. Okay? We have talked about the heat capacity of water, right? A specific heat capacity of water. So there is also something similar for the capacitance, which is how much energy, right, or is related to the amount of energy a capacitor can store. Look, with a capacitor, okay, you can use point charges to study what's going on in a capacitor. I'm just going to show you very quickly before we go into current what's going on with a capacitor. So you have a positive plate and not positive the next one. You need to have a negative plate. If you have that, then you will have an electric field. But how is it possible to have a positive plate and a negative plate? That's when we start introducing the idea of batteries, by the way. So we can plug this in to a battery. Like that. We have devices here in the lab like that, but basically it's just a power supply. It can be a B battery, 9-volt battery. So this is the electric field. And this positive and negative means that this plate has a positive charge Q, and this one has a negative charge Q. Normally there is some distance between the plates. You know what we realized? That if you place a charge here, which is positive, of course, this charge will experiment an electric force because of the electric field. And we realized that by traveling this distance, this force is doing work. So there is work due to a force that actually is conservative. Now, using the definition of electric field, we know that the work done to move the charge is proportional to the electric field, the charge, and the distance. So, you know what? We actually came up with a concept for that electric field and distance, because the charge can be any charge. We realized that there is a potential difference which we call voltage, which is equal to the magnitude of the electric field multiplied by the distance between the plates. This is a formula that you don't need to apply, but just to show you where do we get the idea of voltage. 4 volts, 2 volts, the voltage between a battery. The voltage between a battery normally is due to chemical reactions inside the battery, but the value itself can be used in physical applications. For example, in that one that you see right now on the board, a capacitor and a storing electrical energy, right? So we're slowly getting towards a point where we don't have just point charges sticking there, right? We have a motion of charges, there's a flow of charges, right? So, I mean, the main ideas for this part is more about knowing that there are point charges, that there is a way to quantify the force between them, that each charge can emanate an electric field, and the direction depends on the sign, that like charges repel and like charges attract, right? The force between charges will increase as the charges increase, and if you get them closer, the closer charges are, the more intense the force will be, and the more intense, the more electric field. Looking at that equation there, more force, more field, more distance, less field. So as you go away from a source, you expect, for example, here, if I put my hand here, I will get a spark, right? I will get like a charge. But here, the Van der Graaf. But if I go away from the Van der Graaf, I don't feel anything, right? So this all gets charged. And the applications are, for example, you know where we can apply the idea of this guy, of the capacitor and charges moving, is in the old CRT cathode ray tubes televisions and screen monitors, right? I didn't get to see those, and most of you probably didn't, but you can Google the old televisions that people used to use back in the 80s and the beginning of the 90s. They were big. They were so big that they were so hard to carry on. I believe that was the reason people didn't like to change their televisions, because changing a television back in the day, I'm pretty sure it was a whole deal. First of all, because they were expensive. Second of all, because moving them, and I've seen them, they are very big and heavy. And I believe they made televisions like that up until 30 inches, which nowadays will sound like nothing, right? Like you can have a 65 by nothing nowadays, very cheap. But 30 inches back in the day, 30 inches, right? Yeah, whatever. 30. They were like heavy and expensive, right? But how did they work? The way they work is by having a cathode ray tube, sort of like this. And then the screen will be here. So then in this tube, there will be a capacitor. And then there will be an electric field. The electrons will flow through it. And then at the end of the cathode ray tube, of this tube, they will experience another field that will make them deflect. Right? Because, look, let's erase this one. Let's suppose you have an electron here, and it's going towards the inside this region. So let's erase this for now. There it is. It's going inside. Because the electron has a negative charge, the electron won't be repelled towards there. The electron will be repelled like this. Now, we can adjust the field. By the way, to explain more of cathode ray tubes, we need to understand the idea of magnetic forces. So for now, I want you to accept that the electron can flow without deflection, and then at some point here at the end, it can be deflected like this. And when the electron is deflected, it will go towards the screen, television. And we know already, I explained this, when an electron gets when an electron gets a photon, absorbs or emits a photon, in this case due to an excitation, ionization, it can release energy. It releases a wavelength. And wavelength, you know, it's a characteristic of a wave, right? What you should know is that in electromagnetic waves, a wavelength is a color. Every color has a characteristic wavelength. We will study more that in the next chapter, but for now, let's just say that as an electron crashes towards the screen, the back of the screen, it emits colors. That's what you're seeing. That's why spending too much time in front of the screen, of that screen, and too close to it was actually the reason why some kids got eye problems. Right? Because that was radiation. The electron, by crashing towards the screen, is releasing colors, but also some sort of radiation. It might not be a lot, but enough to recommend people to cover. Back in the day, that's what they said. Computers and televisions, I remember this because in the school where I was, they still had those old televisions, and they would cover them with plastic insulators, right? So the radiation will stay there. And if you had a TV in your room, I remember they used to say that people should cover their screens. Okay, that's the reason why I didn't really see this happening, but I know people I have asked. Let's suppose you have a TV like that or a computer, turn on for a long period of time. Once you turn it off, you think that's it. You could put your hand on the screen and you could feel radiation. If I do that here with this screen, I don't feel anything because this is an LCD. It works differently. It has a different system. All right? It doesn't use cathode ray tubes. All right? So that's very interesting, right? Cathode ray tube is here, B. Okay. C is what you guys have done in chemistry. You guys do electrochemistry and you create salts, solutions in water. So there you are. All right. I believe you use the anode and the cathode for that. To study, to do solutions, to check the mass deposit in the anode. All right, by passing a current. So now we're getting into current, right? So now we're talking about moving charges. What is current? As we have a field, strong electric field, you have a flow of electric charges. So you have a current. The flow of charge per unit time, the rate of change, is what gives you the current. I equals to Q divided by time, coulombs per second, which we define as the ampere. Okay, so that's basically what current is how much charge is flowing per unit time, per second, to be more accurate. All right, so a current of 5 amperes, for example, means that you have 5 coulombs of charge flowing per second, which is a lot, right? The charge of the electron is 1.6 times, oh, by the way, yeah. So in all this, I mean, you don't need to know it, but because it will be given if you need it. But the charge of the electron, guys, which was discovered by Millikan with the oil drops experiment, it's 1.6 times 10 to a negative 19 coulombs. Negative 19, and we're talking about 5 coulombs. So we're talking about trillions, quadrillions, quintillions of electrons, right? So yeah, that's a lot. So there's some devices, and let's see the amount of current they use. Obviously, with the current technology, we have been able to create or develop materials that do not use a lot of current. The more they use, the more electricity, the more expensive is going to be your electrical bill. So a TV nowadays doesn't use as much as before, but it still uses a lot. I will add there hair dryers, yeah, they are in there. I will add the dryer, the washing machine and your dryers, guys. Those things, they suck a lot of electricity. They are like, yeah, not good. Refrigerators, it depends. Some of them, a freezer sucks a lot of current. A freezer, yeah. Your iPhone, not really. Calculator, of course, not. A conventional light bulb, no. But still, video game systems, they do suck a lot of energy as well. There you are. Now, where does the current flows? In a cable. Now, you probably wonder now, or you probably understand now why we have to have rubber or other type of materials covering a copper cable, right? You see copper there, or silver, or gold maybe, or aluminum. Copper will be this one. The insulator protects yourself from getting an electric shock. The conductor has charges all on the surface of the conductor. If you touch it, right? Which is why you can get a short circuit. If you have, that's why you always have to do maintenance. Because if you have a broken cable, you can have a spark that can ignite fire, right? Which is why we have to have very thick cables. Which is why nowadays in every household we have those power bars, right? Because it's easy to, you don't connect things directly towards the wall. Normally, I'm pretty sure everybody here has a power bar, power strip, right? Where you connect and it's easy to turn on and off. So that's important. So there you are. Okay. So remember, a conductor is any substance that allows charge to flow with any complications. Metals, for example, copper, gold, aluminum, all right? They have a very high conductivity and low resistivity. There are liquids such as water that are conductors when they contain dissolved ions, right? Most of the drinking water, however, is neutral. And then there are solid insulators. But there are also insulators that can become conductors when they are wet due to moisture. You have some conductors there, right? But you can also have semiconductors, which are substances that are between conductors and insulators. Okay. I'm gonna finish with the idea of resistance, guys. We've done quite a lot today, almost half of the chapter. We're going to finish with chapter 7 on Tuesday before Thanksgiving, okay? And that means that when we come back from Thanksgiving, we'll start with chapter 8. And I will say that chapter 7 and 8, that will be the topics of your exam. And then chapter 9 will most likely be the last chapter. I will try to discuss a little bit of chapter 10, which is atomic physics, but the main chapters are 7, 8, and 9. Once we finish with that, we can say that you guys have learned what you need to know about basics of physics. All right? And then we can do a review of these ideas. But resistance, guys, is basically the opposition of current. Right? A conductor has a very low resistance, an insulator has a very high resistance. The resistance is a factor that depends on the length of the cable, the cross-sectional area, and a factor called resistivity. Every material has some sort of resistivity. Now, temperature, as I was saying here, with different materials, right, depending where they are, but also temperature allows to increase or decrease the resistance. Normally increases the resistance, right? You remember the linear expansion. If an object expands, the resistance expands, gets larger. So the change of temperature can make a material less conductive. And that's interesting because remember what we said about plasma. Plasma is when gases become superheated and conductors. So that's different though. That's a different state of matter. We're talking about a solid here. In solid, if we increase the temperature, the material gets more resistance. So less conductors, right? In the case of gases, for example, plasma, it was a superheated gas, very conductive. All right. So we can talk about superconductivity later, and then what's next? Yeah, we can talk about Ohm's law, and that's almost basically what we need to go over, and then circuits. All right, guys. So we will finish with chapter 7 on Tuesday. We did more than what I think we're gonna do because I was a bit late, but that's good. As you can see, there is not a lot of math. I will show you Ohm's law and how to use. It's a very simple equation, by the way, and then it's gonna be more conceptual than anything. Okay. Again, we will finish chapter 7, Ohm's law, circuits, and power next Tuesday, and then we have the Thanksgiving break, where after that we will do chapter 8, right? So if I was to think about when we're gonna finish chapter, or when we'll have exam number 3, exam number 3 should be this week, the second week of December. Then we can talk about chapter 9 and have the final. Actually, you guys are still here, so here. Hopefully I can go to my email. See, final exam. Okay. So our class is Tuesday and Thursday between 3 and something, right? So here. Ooh. Let me see here. Okay. So we have to do a change. Actually, no. Exam 3 can be on Tuesday, and we review on Thursday then. The final exam, according to the calendar here, will be December 15, guys. Okay? Almost 3 hours, from 3:30 to 6. You won't need all the time because the exam won't be that long. Okay? So write down your calendar, guys. All right, I'll see you guys on Tuesday. Take care.
Thank you, Professor.